Hi, welcome to my 2CM4 design project. Today we're going to be designing a passive straight fin heatsink um, with no airflow. And what we're going to be doing is exploring the relationship between the width of the fins and the overall heat dissipation of the heatsink. To quantify the heat dissipation, we're going to be measuring the heat flux through one of the planes. Here's the image of a heatsink. Essentially, the purpose of a heatsink is to um, it's a thermal management device, and it kind of just dissipates heat away from any device that you kind of put it on or put it next to that's going to generate heat. And yeah, so just to start off with some of the physics that we're going to use, we're going to be using the steady state heat equation, which is essentially just a full heat equation, but since the time derivative of temperature is zero, we're going to be making that steady state assumption. It's just going to simplify to this equation here, which is what we're going to input into flex. We're also going to be using um, convection, um, which is going to essentially model the air around the heatsink, and we're going to apply it to a boundary condition and just measure the rate of heat transfer due to convection. And heat flux we're going to use to model or kind of to measure the how well the each heat sink is going to dissipate heat. And we can see here that it's dependent on the conductivity and the time derivative of temperature. Sorry, the gradient of time derivative of temperature. And because there's a negative sign, we know that it's going to point from the high temperature to low temperature. So sort of along the temperature gradient. Yeah, so this is the model of the um, the heatsink that we created. It has only four fins, so it's going to be it's a simpler model than it's sort of a simplified version of a heatsink because Flex doesn't allow you to make super complicated geometries. Yeah, so what we have here is so this so the way we're going to be measuring heat flux through this part through the heatsink is we're just going to look at the y equals 1 plane and just measure the heat flux through that in 3D. So it's going to go from like basically there to there. And yeah, and the sort of the heat is going to be applied to the whole bottom face of the heatsink. And yeah, so this is kind of this over here. This is how we created the sort of the geometry and then extruded it into the z direction. This is the time independent steady state heat equation. And yeah, so first we started off by doing a test case for a 1 meter fin width. This is the temperature contours. There's a few more. This is the z equals 0 plane. This is the bottom face, so it's all just at 100 degrees, and that's kind of the side view, and you can see the temperature distribution. This is a vector plot on the z equals 0 surface, and it shows you the direction in which the heat is traveling. Yeah, so the heat flux for the 1 meter fin width was about 80,000 watts per meter squared. We also did measurements for the 3 meter and the 2 meter one. For the 3 meter one, it was 44,000 watts per meter squared. So we can see as you increase the width of the fins, the heat flux decreases. So essentially from that, we kind of know that it's going to be an inverse relationship. And to maximize the um, the heat the heat dissipation, we're going to have to minimize the fin width. So we go ahead and we script it into Python, and we see it's an inverse linear relationship. So essentially, as fin width is going to increase, the heat flux is going to decrease. And since we're using heat flux to kind of tell us about the heat dissipation, so essentially for the to optimize heat dissipation, we're going to have to decrease the fin width. And the reason I think this is because um, as you're increasing the fin width, because of the geometry of the heatsink, as fin width increases, the surface area to volume ratio is going to decrease. And essentially, because the heat is traveling through the object, what we want is the and volume ratio surface area to volume ratio to be as high as possible. And to do that, we need to, and for our geometry, we need to minimize the fin width. And yeah, so this is just kind of how we can visualize the relationship. And yeah, that's pretty much it. Thank you.